Well, let's start our third class on complex number after a long gap. So far in class 1 and class 2, we have studied complex number, what is complex number, and in class 2, we have studied extensively the polar representation of complex number and its argument, amplitude, and certain problems and certain formulas, certain properties of argument and modulus, etc. So now we are going into certain integral powers of complex numbers. So let's start with that. All right. So first, integral powers of complex numbers. Integral powers means something to the power some integer. It's called integral power. Okay. Just like the real numbers, complex numbers do behave exactly like the real numbers. Like if you put z, any complex number, z to the power 0 is 1, just like the real number. Z to the power n is same as z to the power n minus 1 into z, exactly the real number. To the power minus n, okay, minus n means it's on the denominator. Okay, it's going down. So z must be a non-zero number. So if it is 0, you cannot put it back on at the denominator. So if z is non-zero, then z to the power minus n is same as z inverse. That means 1 by z to the power n. Okay. Now some other rules of indices, like if you multiply z to the power n, z into z to the power n, the same complex number, then it turns out to be z to the power m plus n. Z to the power m first and then whole to the power n is zmn. And similarly, okay, I'm sorry, it will be to the power m. Z1 to the power m, Z2 to the power m is Z1 into Z2 whole to the power m. It will be to the power m. Anyway, I will rectify it in the class note. All right. So far these are almost same as real numbers. So now let z be a non-zero complex number and q be a positive integer. Then what is z to the power 1 upon q? Now for real numbers, suppose 2 to the power half. You know what that is? That is barely square root of 2. Like 2 to the power 1/3 is merely cube root of 2. Similarly, z to the power 1 by q is a complex number for which w, so that w to the power q is z. Exactly same as root 2. Suppose root 4 to the power half is 2 and minus 2. So 4 to the power half is a real number for which if you raise power 2 to that, you will get 4. Similarly, omega is the real number, w is a real number. If you take the raise the power q to it, you will get z. Now, w is called the cubed root of z. This is exactly what is our topic of the discussion. The cubed root of or nth root of complex numbers. How do they look like? All right. So, let's start with a complex number, a non-zero one, and n be a positive integer. Then we will our aim is to discuss what is z to the power 1 by n or the nth roots of z. All right. So let's start with the polar representation of z. Suppose the polar representation is r cos theta plus I sin theta, where r is the modulus. So modulus, as you know, it's the distance of the complex number plotted on the two-dimensional plane from the origin. So this being a distance, it will always be positive. and theta is the argument or amplitude. So theta, as you know, there is a restriction on theta. We have already discussed it. It is between minus pi to plus pi. So you are not allowed to cross the negative side of the imaginary axis. All right. Now, suppose z to the power nth root be some complex number w. Then, as it is a complex number can be written as a in a polar representation. So suppose it is rho cos psi plus I sin psi. Okay. Then omega to the n, w to the n is z. Well, now what is w to the n? W to the n is merely this whole thing to the power n. So definitely it is rho to the power n, and the inside part, this is something that we will prove or discuss in the next section. But so till then we just uh, assume it that this part cos psi plus I sin psi whole to the power n is cos n psi plus I n psi. Okay, it is easy to prove using mathematical induction, and we will prove it in the next section. So this equation, this one w is z to the wn is z, now turns out to be this. Now this is a complex number equal to another complex number, so the two complex number are the same. That means the real part of the both side and the imaginary part of both side are the same. So real part is same as real part on the right hand side, left hand side imaginary part is left hand side, right hand side imaginary part. So if we equate them, then definitely we get rho to the n is r. Now, then rho is r to the n. Now r is a real number, so this is r to the n, 1 by n is merely the nth root of r. Now there can be n different values. As you know that the square root has 2 values, cubed root has 3 values. Similarly, nth root has n values. So r to the power 1 by n definitely will have n different values, but there will be only one value which will be positive real. Other values can be either negative or imaginary. All right. So we will consider only the positive value of r to the power 1 by n. There will definitely be one positive real value of r to the 1 by n, and we will consider only that, because rho, as we know that rho is also a modulus. So rho cannot be negative or imaginary. So rho must be a positive real number. So among the n roots of r, we will consider only the positive nth root of r as rho. Okay. So as long as the rho value of rho is concerned, that is done. That part is settled. Now let's come to the psi part. So if we equate these two equations, then we get n psi is theta plus 2k pi, where k runs over any integer. Now, why theta plus 2k pi? As you know that sine of theta plus 2k pi is sine theta itself, and cos of theta plus 2k pi, cos of this thing is merely cos theta, sine of this thing is sine theta. So in general value, the general solution will be this to be theta plus 2k pi. So k runs over all integers. So there are infinitely many possible values of n psi. Theta as well as theta plus 2k pi, where k runs over an integer. So psi has infinite many values, and that's psi is 2k pi plus theta by n. So there are infinitely many possibilities for psi. So thus, as psi has infinitely many possibilities, so w has infinitely many possibilities. The possibilities are r to the n, which is only one possibility, but cos 2k pi plus theta by n, I sine 2k pi plus theta by n, where k runs over the set of all integers. So this is where you get infinitely many possibilities for w. Well, But now, as we will keep on discussing, we will actually see that there are not infinitely many, there are only finitely many. So we are going towards that. So let us now set some certain notation for our simplicity. For k equals to m, let us denote the value of w for k equals to m to be w suffix m, to be like that. Just replace k by m, and that's the notation for wm. Okay. Now, next we shall prove that there are only n distinct values of w, which are wherever, even if k runs over all the integers, there can be only n distinct values. The values are w0, that means corresponding to k equals to 0, k equals to 1, k equals to 2, up to k equals to n minus 1. These are the only n distinct values of w possible, even if k runs over an infinite set of integers. Okay, so to prove that, first we have to prove two things. So we have to prove two things: n distinct values, and they are all. So first we show that this omega 0, omega 1, w0, sorry, w0, w1, w2, and wn minus 1, they are really distinct. And in the next step, we will show that as k runs over any real number, any integer, then the values other than k, for the values of k other than 0 to n minus 1, the value corresponding to that will eventually fall into this set. Okay, the first thing first. So first let us show that this w0 to wn minus 1, they are actually distinct. Okay, so let's take two things, two values of k. So let us, if possible, they are not distinct. So we will prove it in a method called method of contradiction. So in this method, you must have seen earlier also. In this way, to prove something, we will assume the contradiction of that, and finally we will arrive at a contradiction to a standard fact. Okay, which eventually let you know that whatever we have assumed is actually wrong. So that proves the result. So if possible, let us assume they are not distinct. Let us take two, the wp and wq, where pq are within the set 0 to n minus 1 for the values of k, and as they are two different integers, so one of them should be greater than other one. So let us assume that p is greater than q, and they are equal. If they are equal, then we will write their polar representations, and the row part will will cancel out, and we will be left with these two equations. This is for wp, and this is for, if we equate the real part and imaginary part, this is the for wp, this is for wq, this is for wp, this is for wq. Now these two equations together will give you that this value is nothing but this plus 2si, where s runs over any integer, as we did earlier. Now it actually gives you that if you take this on this side, we'll get p minus q by n as an integer, because pi will be cancelled out, and we will see that this will imply that p minus q by n will be an integer, merely this 2s, you know or s maybe. So if this is an integer, then it is only possible when p equals to q. Why? Because p minus q is less than n. P minus q, p is greater than q, so p minus q is definitely greater than 0, but it cannot be more than n, because both are less than n minus 1. So p minus q is definitely less than n. So if it is less than n, and n is sitting at the denominator, and if this guy has to be an integer, then the numerator should be 0. That's the only possibility. other other than any other than 0, if you put anything positive over here, then this will be that will be less than n, and that will be a fraction, and which will not be an integer. So definitely p minus q has to be 0 only to be an integer. So if p minus q is 0, then p has to be same as q. But we have assumed that p is greater than q. So this actually contradicts our assumption. So hence what we have assumed that WP is same as WQ for P greater than Q and within this range is not correct. So what thing will be wrong? That WP must be different from WQ. So they are distinct. That part is proved. Next, we have to show that let us take any key other than this set. So other than 0, 1, 2, and minus 1, let's take any k. So if it is not in this set, then it must be either n or anything more than that. So let's take t, let's take value of k to be t. T is an integer which is more than n minus 1. So if it is n, either it is n or anything more than n. So if it is n or anything more, then there is something called division algorithm. So division algorithm is you will learn division algorithm in classical algebra of numbers, real numbers. But I can tell you on a nutshell that as t is more than n, now try to divide t by n. So what will happen if you try to divide something by n? Then you will get something remainder. You may get some remainder. Either it will be 0 or there will be something which will be less than n. So basically it means if you divide t by n, you will get something here and some remainder here. This is the remainder. Okay. So, so t can be written as something into some lambda into n plus something remaining q. So this form of writing is called division algorithm. You will learn it in details anyway. So by division algorithm, as t is more than or equal to n, so t can be written as lambda n plus mu, where mu is less than n because it's a remainder. So it can be 0 or can be less or equals to n minus 1, and lambda is an integer, of course. So if t can be written in this fashion, then let's write wt. Now it's routine checkup. You just put the value of t in this fashion, and it turns out to be wt to be w mu, where mu is lying between the value of 0 to n minus 1, and w mu definitely belongs to the set from w0 to wn minus 1. So anything, any value of k other than or more than n or anything more than that will, the corresponding value of wk will be one of the values of w0 to wn minus 1. So w0 to wn minus 1, they are the n distinct nth roots of the complex number z. Okay, so we sum up this here, that the n distinct values of z to the power 1 by n, nth root of z, are basically they where k runs over 0 to n minus 1. And note that the value corresponding to k equals to 0, which is very as a primitive value, the first value for k equals to 0 is called the principal value of z. Now, all right. Now let us look at the geometry behind the roots. This is very interesting. After a long discussion, you can see you're starting with the complex number z, whose amplitude is theta. And now you are looking at the nth root of that complex number, whose the modulus is r and amplitude is theta. Okay. So the values, as you can see, they have the same modulus. The roots, they have the same modulus, r to the power 1 by n. So that means all the complex number, the roots, all the roots, they are lying at the same distance from the origin. So they lie on a circle around the origin whose radius is r to the 1 by n. Right? This is number one. So the roots of the complex number lie on a circle, and the circle is of distance r to the 1 by n. Number one. Number two, theta is the argument of the complex number z. So the the principal nth root of z will be this complex number, which makes an angle theta by n with the x-axis in a makes an angle theta by n in the positive direction with the x-axis or the real axis. So this is the first principal root of z. So the distance is r to the 1 by n, and the angle that it makes is theta by n. So you know theta, you know r. So the principal root will be the point where it makes an angle theta by n in a positive direction from the real axis. And then the other roots are very simple. Now you divide 2 pi by n. So 2 pi by n. That makes an angle. That's the value of an angle. And now you just keep on rotating this principal point, this complex number, the point is the root, through an angle 2 pi by n. So if you first rotate it, then it will get the second root. That's the corresponding to k equals to 1 root. If you rotate again by 2 pi by n, you will get through along the circle, then you will get the third root. So that is corresponding to k equals to 2. So k denotes then how many times you are rotating through an angle, the rotation you are giving by an angle 2 pi by n. So this is a single time rotation for k equals to 1. That means one time you are applying 2 pi by n rotation. For k equals to 2, you are applying 2 times in 2 pi by n rotation, and you are getting this point. Similarly, if you keep on rotating this thing by 2 pi by n angle, so you will get, and up to how many times you will rotate? Up to k to be n minus 1. So, and that will give you the n roots lying on the circle around the origin. So basically the roots are rotating. The getting the principal root is the important thing, and then simply keep on rotating through an angle 2 pi by n, and you are getting other roots of the complex number z. Okay, all right. Now let us look at the complex number. Next we shall concentrate on the complex number the complex number, not it's a real number, but you can consider it as a complex number 1. Okay, so that is called the 1. As we have already discussed, the real numbers are also complex numbers. The real numbers can also be considered as complex numbers with the imaginary part to be 0. So 1 is such a number that is, if you multiply 1 to any real number or complex number, you will get back that number. So 1 has this property, and that is why 1 is called the unity, you know. So that is why 1 plays a very important role in the algebraic structure of complex number as well as real numbers. So the nth root of 1 are really of special interest. So next we will discuss about the nth root of the number 1, the real number 1. Okay, that will be done in our next class. I am not overburdening you with more than one topic in one class. So that will be done in the next class. Thank you.